Hello, everyone. Good evening or good afternoon, depending on what time you are listening to this recording. This is a continuation of our physical lectures that we've had. I've decided to record it because last week there are so many things that were happening and I was not able to make it for a physical lecture. That is why I've decided to just prepare and record the video for you. So that we can make up for the lost time that we couldn't make on, last week. So welcome once again. This lecture is about servos and actuator systems in optical heads. This is our main focus today: the servos and actuator in optical heads. So first and foremost, I want us to just define what a servo system is, so that it will become easier for us to understand the different servo systems within the optical head. So a servo system is defined as an automatic control system used to control rotation angle or displacement of a control object. So in our case, our control object is a laser spot, so that it can automatically, continuously, and accurately re-enter the input command. Remember, when we are talking about an optical head, we are talking about two things: either reading or writing, and those two things they are supposed to be done continuously. So for that to be achieved, a servo system must be in place so that it can do that automatically, continuously, and accurately. So a servo system is basically referred to as a closed loop system. A closed loop system is a system that has an input command and an output command, and the output is continuously being compared with the input, for a simple reason that if the desired output is maintained or is achieved, then a feedback system, there will be a feedback system to compare the output with the input. So if the output is the same as the input, then it means there is no error. And if there is no error, that means the process will just continue. But if, say, for example, in the case that we are talking about, a laser spot, we have already discussed how an optical head looks like, the incident path of the laser, how the laser beam travels from the laser diode to the collimator, the split beams, and so forth until it gets to the optical disc. So here, if the laser spot is supposed to be on a specific track, at the center of a specific track, then that is what is desired. So if it happens the laser spot is slightly shifted, then the system will send an error. So that error will mean that the laser spot is not correctly focused, and then it will shift. So a closed loop system basically compares the output with the input continuously. And when there is no error, then the command, either read command or write command, will be affected once there is no error. So a closed loop system is basically represented in a block diagram, like what you can see here, where R is the desired command, E is the error that is generated after the output is compared with the input, and H is now the process. This is where now we have the split beams, the objective lens, the positionings, and the angles and everything in such a way that if the output shows that there is an error, that error could be maybe the lens is not positioned properly, then proper action will be taken in terms of actuators. Now, this is where the actuators come in. The actuators will now correct. If it is a wrong positioning of the lens, the actuator will position it properly, and then the output, a new output will be sent. So until that point where we have an output that is directly the same as the input, and then the other process will follow. So a closed loop system works that way. The output is continuously compared with the input. And if there's no error, then the command, the command of reading and writing will continue. So we'll see different servo systems within the optical head that ensures that information is not lost or is not tampered with during the reading, writing, or recording processes. So for an introduction, in optical disc systems, the laser beam must be focused accurately on the disc track. Typical systems require the beam to be focused within 1 micrometer on the information layer and to be positioned on track center within 1/10 of a micrometer. So this is what is desired for the reading and writing processes to take place. That the laser beam must be within 1/10 of a micrometer. So it cannot be outside the track by maybe 0.2. That will indicate that there is a problem. Meanwhile, the axial and radial runout of optical discs are 2 to 3 orders of magnitude larger than allowable focus. And tracking errors, an optical head cannot be guided mechanically or aerodynamically by the disc. So what it means is, despite the fact that a laser spot must be within the track to within 0.1 micrometers, the movement of the optical disc is much larger, 2 to 3 times larger than the requirement, which is the 0.1 micrometer. So what does it mean? You have a requirement that is very accurate, 0.1 plus or minus 0.1 micrometer, but you have a disc that slight can shift by even one micrometer. Radially and axially. These are two terms. Probably radial run out means movement across the radius, like along the radial line. So when a disc moves along the radius line, then that means the laser spot is moved outside the track. All right. At the same time, axial movement, you have a disc that is rotating. That means it can move up and down. And the moment it moves up and down, it means the focus of the laser is interfered with. So the big question is, if the requirement for a focused laser is 0.1 micrometer, and we have the disc moving about one micrometer radially or axially, how is it possible to ensure that a laser spot is always on the right spot within the track? That question is answered through what we call the servo systems. The servo systems ensures that if the disc shifts slightly, either radially or axially, the laser spot does not lose the track. The laser spot does not lose the track, because if it loses the track, then it means information will not be read or written properly. The other thing is this, that what should be the speed? What should be the speed of the optical disc? Because if there's movement in the disc, then the laser spot must respond very fast. It must not give time for error, that the disc moves and then the laser spot is focused on a different track. It must be faster. It must be faster than the disc, so that the laser spot is maintained. So the thing that I'm trying to drive across here is that movement of the disc, either radially or axially, must be followed by the laser spot accurately. There is no time that the disc will leave behind the laser spot. And to make sure that that happens, the optical head has what we call the servo systems, and we shall look at those servo systems and how they ensure that the laser spot remains on the track and it is reading what it's supposed to read. So as a result, the disc needs to be actively followed. Yeah, that is the word that I was trying to say, that the disc cannot leave the laser spot behind. Even if it moves up and down, the laser spot should be faster than it. It's like the shadow. You know, you cannot, there is no time you can leave your shadow behind. Yeah, so in this case, we have a spot that should always be the track, regardless of whether the disc moves outwards or up and down, the laser spot must be there. And that requires a very good design, optical and mechanical design, to ensure that the laser spot is always on the track. All right, so although spot or beam positioning in principle would only require a focus and a tracking servo, tracking is almost always performed with two servo loops working interactively. At this point, let me explain that because we have said that the spot must be on the track within the correct distance at all the times, so we have two servo systems. We have one servo system which is known as the focus servo, which monitors the movement, up and down movement of the disc. It's called a focus servo. And then we have a tracking servo, which monitors the outward and inward movement of the disc. The radial movement is called a tracking servo, to ensure that the spot is always on the track. So these are two things. These are two servos that we shall continue, we will repeat, we will keep talking about these two, the focus and tracking servo. And then the actuators, whatever does now the positioning, is called an actuator. There are two types. We have the fine one and we have the coarse one. It starts with the coarse one and then the fine one that will now position the laser spot directly at the center of the track. So first of all, it is to identify the track. That is the coarse tracking actuator. Once the track has been identified, then we have now the fine actuator that will position the track directly on the center. All right. Since the tracking servo system is usually not capable of performing random track access, the fine and coarse tracking actuators are driven over multiple tracks by another servo system called the seek loop. The seek loop basically identifies the right track. Once the right track has been identified, then we have the coarse tracking actuator and the fine tracking actuator, ensuring that the spot is directly in the center. The diagram here just tries to illustrate. You can see the laser spot there, which is black in color. And then we have those recorded marks, which are in gray in color. So the laser spot must be within. You can see the laser spot there is within that line so that it can read those bits, whether it is 0, 1, 1, 1, and so forth. But then we also have the perforated servo marks. The perforated servo marks is what now the system uses to help locate the center, of the servo. Well, at this point, I've not started going into the specifics, but when we start looking at now the specific, we will see how it is possible for the focus servo and tracking servo to work interactively to ensure that the laser spot is always at the center of the track. So this diagram shows just an optical head, the components that are there, and the type of movements that I have just tried to explain here. You see these two black arrows. There is one pointing, there is an arrow pointing the direction of rotation of the disk. So the disk is rotating in this direction, but we also have a tracking servo which is pointing perpendicular to it. So the tracking correction simply locates the correct lane or the correct track. And of course, we shall talk about focus servo later. The focus servo monitors the up and down movement. So we have up and down movement, and we have the radial movement, which is now the tracking correction. So all these other components we have already discussed, from the laser diode, the collimator, the beams, the beam splitter, mirrors, and so on. And then, of course, we have a photodiode, which plays a very, very important role when it comes to the tracking and focusing servos. This is one thing that we will explain in detail when we reach there, the photodiode. But at this stage, I just want us to appreciate that you can see the focus actuator, which I've said monitors the up and down movement. And then we have a tracking actuator, which moves across different tracks to locate the correct track. So in the tracking operation, the moving part or the tracking actuator, which has an objective lens and a focusing actuator, is driven radially to the target track, right? Okay, I think that's common sense because tracks are normally concentric. And so for you to locate the correct track, you must have the laser moving along the radius. So that is what we're talking about, that the tracking actuator moves radially as it locates the correct track. It is first coarsely positioned. That means it is just generally positioned around the correct track. Then once it is coarsely positioned, then we have a fine actuator that will now do the adjustments until the laser spot is directly on the center of the track. So it is first coarsely positioned to the vicinity of the target track, with an accuracy of plus or minus 1 micrometer. Next, it is finely positioned. It is finely positioned by a fine actuator, such as a galvano mirror, with an accuracy of plus or minus 0.1 millimeter. Maybe a small analogy. When you want to scratch your head, you first of all take your hand to that area. You first of all take your hand to the area, and then once your hand has landed on the correct area, your finger will now scratch. So the finger is like the fine actuator, and your hand is basically the coarse actuator, because it takes you to your head, but the finger will now scratch the specific position. The diagram here tries to emphasize that we have a tracking actuator with an objective lens and a focusing actuator mounted radially. So we have radial movement and we have axial movement. In this tracking operation, most of the time is spent on course positioning. Therefore, course actuators are developed with the capability of fast positioning and accuracy of within plus or minus 1 millimeter. I think we are getting the point that the tracking servo is the function is simply to locate the track. Is simply to locate the track, and to locate the track, it has to be done first with a coarse actuator and then followed by a fine actuator. So the diagram that you can see there is a bit faint, but it contains what I want to show. It's basically the same as the diagram that we had, but here we have a block diagram that contains the laser diode. We have a collimator lens. We have anamorphic prisms, which we already have what we have already discussed what it is. Then of course we have an objective lens, which is reflected towards the optical disc. The optical disc you can see down here. But what is important here is that we have an objective lens just near the optical disc. The objective lens is very, very vital when it comes to focusing the spot on the right track. That is the axial focusing. But again, the other beam goes through the polarizing beam splitter, a cylindrical lens, and then it gets to a sensor, which is referred to as a quadrant photodiode. All right. This quadrant photodiode, there are two of them. We have A, quadrant photodiode A, and we have quadrant photodiode B. The two photodiodes, the quadrant photodiode A is meant for to track the focus. That means if the disc moves away from the objective lens or towards the objective lens, that will be monitored by this photodiode A. If the disc moves away in terms of the radius, if it moves radially, then that will be determined by the photodiode B. Then we have a differential amplifier, which is just to compare the signals and to convey an error. It conveys an error whether there is no error or no error, and so on. So this diagram, the important things here are the photodiodes and this objective lens, because this is what we are going to focus on so much when we are explaining the tracking of the tracking servo and the focus servo. Yeah. So a magneto-optic recording head contains a large number of discrete components. We have already seen those components. Since a laser diode emits an elliptically shaped beam, some means is typically used to circularize or to make them circle, to circularize the beam after collimation by a collector lens. This is done by an anamorphic prism, which we know there are two prisms which are trapezoidal in shape, and so they also function as a beam shapers. They expand the beam and they also shape the beam to have it in circle form. After passing through the anamorphic prism and a beam splitter, the laser beam is focused by an objective lens through the transparent substrate on the magneto-optic disc onto the magnetic film, in which the information is stored in the form of reverse domains. So this sentence is basically explaining the movement of the path taken by the laser beam. which I think we have already discussed in detail. After reflecting off the disk, the light returns to the beam splitter and is deflected towards polarizing beam splitter. This polarizing beam splitter is set at 45 degrees to the incident. So this information here we have already discussed, and you can actually read that and track what has been written to this diagram here, where you have the beam splitter, the collimator, the anamorphic prisms, the objective lens, and so on. But now we are getting towards the servo system. So a photodiode sensor, we remember we have said there are two of them. One is to track the focus, the other one is for tracking the servo. And that if there were no rotation of the plane of polarization of light by the disk, 50% of the light would go to each quadrant photodiode. I will go back to the diagram to explain this. That if there are no rotation of the plane of polarization of the light by the disk, 50% of light will go to each quadrant photodiode assembly. By summing the signals from each quadrant photodiode and differentially detecting the sums from each quadrant photodiode assembly, the output would then be 0. If a magneto-optic signal, however, if the signal at one quadrant photodiode would go up by a certain amount, delta, while the signal at the other goes down by the same amount, thus the differential would be 2 delta. Now, let me just try to explain. This quadrant photodiode, there are actually 4 of them. If the intensity of light in one half is 50% and intensity in the other is also 50%, then it means the intensity is balanced. And in that case, there is no error. It simply means that either the spot is in the right track or the spot, the disk has not moved away from the objective lens. So that's what we are talking about here. That if, for instance, you have in one quadrant, you have more light. The intensity of light in one quadrant is more than the intensity of light in the other quadrant, then it means there is something that is not correct with the focus. Either the disk has moved far away from the lens, or it has moved too close to the lens. And in such a case, an error signal will be generated. When an error signal is generated, then corrective measures are taken. For example, if the disk has moved away from the lens, then the corrective measure would be the lens will have to be moved closer to the disk so that the spot is always maintained within the track. So an example has just been given here that if one quadrant goes up by an amount delta, then it means the other quadrant will go down by an amount delta. And so the difference in light intensity between those two quadrants will be 2 delta. And because of that difference, it means there's an error. All right. This differential detection system also cancels out the first order, all intensity variations which arise from the laser or changes in reflectivity of the disk. So let me explain now in detail so that we see the intensity that we are talking about. For the focus control, we have a focus control. Remember, focus control is monitored by what we call the focus servo. A focus servo, that is the control system that monitors the up and down movement. So in this diagram here, if this disk moves slightly up or lower so that it interferes with the distance between the objective lens and the disk, then an error is generated. But the question is, how is that error coming about? That error is monitored, using the first quadrant photodiode. A photodiode is simply a diode which passes current when light falls on it. There are several diodes, but specifically for sensing light, we have a photodiode. We also have diodes that emit light. Those ones are called light emitting diodes. But for sensing the intensity of light, we have these photodiodes, which is in 4 quadrants. So let me go to the specifics. If the disk position is maintained relative to the objective lens, okay, if it is maintained, if it is 0.7 micrometers, if it is continuously 0.7 micrometers, then the photodiodes will have a spot at the center. The detectors, the photodetectors, will have a spot at the center, and therefore an error signal will be 0. But how is the error signal generated? We have light intensity in quadrant A1, we have light intensity in other quadrants. So we take A1 plus A3, subtract the other ones, which is A2 and A4. In other words, we take diagonal intensities. We take diagonal intensities, and for a simple reason being that if the disk happens to have moved slightly away, if the disk happens to have moved slightly away from the objective lens, then the photodiode will not record a spot at the center. Instead, it will show an ellipse. It will show an elliptical beam. It will show an elliptical beam, and that elliptical beam is either aligned along A1, A3, or it's aligned along A2, A4. That is why the focus error signal is obtained by subtracting the diagonal intensities. I believe that is clear. If the disk moves a bit closer, then again the beam will be an ellipse, and that ellipse can be along A1, A3, A2, A4, depending on whether the disk has moved closer or a bit far, right? So that is the main function of the photodiodes, to detect the position of the disk in terms of outwards or inward movement. However, when the disk is too close, I think I've explained this, but let us just see. However, when the disk is too close or too far from the objective lens, the light will no longer focus on the aperture of the cylindrical lens, and the quadrant photodiode detector will be illuminated with an elliptical beam. So if you look at the cross-section of a quadrant photodiode shown there, we have two ellipses. If it is too far, then the ellipse will be along A1, A3. If it is too close, then the beam will be along A2, A4. And so you will find, for example, that if it is too far, you will have intensity A1, A3 being greater than the sum of A2, A4. And because of the difference in intensity, that will give you an error. That error is called focus signal error. It is showing that there is a problem with the focus. The disk has moved far or close to the objective lens. And when that error signal is sent, then actuators, we have what we call actuators, and one of the actuator in this case is called a voice coil assembly. I'll explain this a little bit more, and I think in my next slide. So an actuator will either move the objective lens closer or far away. so that the laser spot is not lost outside the track. Okay. Now, before I go to track following, I think the focus servo system is well explained in terms of movement of the disk. If the disk moves too away or closer, an error is generated. When an error is generated, an actuator will take action either to move the disk. I mean, sorry, not the disk, but the lens, the objective lens, closer or far so that the spot is not lost. But I just want to explain a little bit more about the voice coil. The voice coil assembly. Now, I want to assume that we all know how a loudspeaker works. A loudspeaker normally has a permanent magnet, which in most cases has the poles north, south, north. And then we have a coil at the center. We have a coil that is wound on the center magnet. So in that coil, if current passes through the coil, the interaction between the magnetic field lines and the current will bring in a force, which is governed by the Fleming's left-hand rule. That force can either be outward or movement depending on the direction of the current. It is the same scenario here. The only difference is we do not have a fast varying current. For example, if the disk has moved too far, it may send a positive error. A positive error would mean that maybe a current of 0.1 is sent to the voice coil, and when the current is sent, there will be a force that will push the coil maybe outwards. So the objective lens is attached to that coil, so that when it moves outwards or inwards, it is correcting that error. All right. If the disk moved too far, then the objective lens will be forced to move closer, and that movement is done through the voice coil assembly, which I've explained. It has almost a similar mechanism to the loudspeaker operation. So now we are on to the track following. Remember, we had explained that there are two photodiodes. We have the focus servo photodiode, and we have the tracking photodiode, which is photodiode A and photodiode B. Now, for the tracking, the beam that is coming from the objective lens is diffracted by the optical disc. All right. I want us to get that clearly. It is diffracted. Diffraction simply means spreading of light or beam due to obstacle or an opening. Now, because the disc has grooves, it has grooves along or on the perimeter of the track. When a laser beam is directed onto those grooves, it is diffracted. And diffraction brings about several orders of diffraction. We have zero order diffraction, we have first order, second, and so forth. So what happens is this. If the laser spot is directly on the center of the track, remember we are talking about tracking servo, the one that tracks, let me not use the word track, the one that monitors whether the spot is on the right track. Now, the diffraction orders, they interfere, so that if the spot is on the center, the interference caused by the zero order and the first order. The zero order and the first order will appear something like what you can see on the screen there. You see, the diffraction comes in terms of cones. It comes in shape of cones, so that we have a zero order cone and we have a first order cone. When those two cones overlap, or what we call interference, it will appear on the photodiodes as two, look at the diagram here. It will look at two dark ellipses on the two diodes. So in this case, when it appears like this, it means the laser spot is directly on the center. If the reverse happens, assuming that the laser is not on the track, then what will happen is that one side of the quadrant will have an ellipse, the other side will not have. And because of that, the intensities will not be the same. And if intensities are not the same, it will generate an error. When an error is generated, then action is taken. If the disk has moved radially away, then an actuator will bring it back, because there's an error that was sent to show that the disk has moved away or inwards. Remember, these things takes very fast. It is faster than the rate of reading. The reading cannot be faster than the speed of the actuators. The actuators must be very fast so that they correct or they position the optical disc before a laser spot is directed for reading and writing processes. So this diagram here tries to explain that in tracking, in the tracking servo, it is based on the diffraction. It is based on the diffraction, and that diffraction brings interference from the zero order and the first order beams. The interference now, the way they appear in the photodiode, if the intensities are balanced, it means the laser spot is on the track. If one side has a beam and the other side does not have a beam, then it will generate an error. So when the beam is centered directly on a group between two groups, the two first order beams are identical and they interfere equally with the zero order beam. However, when the beam is off center, I'm just reading what I've already explained. When the beam is off center, they interfere differently. By aligning the quadrant photodiode detector so that one first order beam falls on the left half of the detector, B1, B4, and the other falls on the right half of the detector, B2, B3, one can then derive a tracking error signal from the difference. This tracking error signal can then be used to control a voice call assembly to translate the objective in the radial direction. So then we have the actuator moving the objective lens along the radial line. Okay, remember for the focus servo, the actuator moves the objective lens upwards or downwards. For the tracking servo, the objective lens is moved along the radius because it simply means that the disc has moved away from the center. So the objective lens has to follow what the disc has done. Okay, due to tight spot requirements and large services, so this is basically the requirements, or we are basically talking about the requirements of a servo system. Due to the tight spot position requirements and large disturbances, high gain focus and tracking servos are used with bandwidths of multiple kilohertz, right? So here, the emphasis is to show that the servos must be faster. The servos must be faster than the reading speed. This can be challenging because complicated interactions may exist between the three servos and the three actuators. So the challenges that come with the coupling optical and mechanical systems is that if it is not done correctly, then the system will not be robust and reliable. Something robust is something that when it works even for a long time, it does not lose the quality. But if it only works for a short time and then it produces error all through, then it is not robust. All right. The other challenging issue is that the development of a dynamically well-behaved actuator and structures. So an actuator must be very dynamic so that it tracks the speed of the movement of the optical disc. It can track it without losing it. Then, of course, the interaction between the optics and mechanics is also a challenge. So these are challenges that are associated with the servo systems. So the servo loop contains three things. We have said a sensor, which is a photodiode, an actuator, which is a moving coil assembly, and we have a loop controller, which is basically the system of mirrors and lenses which sends information. So optical head sensors have been explained there. I'm just looking at what I have not explained. So we have a sensor and actuator. Okay. And actuator, of course, because it's magnetic. The Fleming's left-hand rule depends on the magnetic fields, the current, and the length of the conductor. So that is guided by that formula. And of course, because it is also positioned in such a way that it's resting on some spring, then the Newton's law and the Hooke's law must come into play. But I think this kind of it depends on the arrangement. Usually, the objective lenses are aligned in such a way that the gravity acts on it going downwards. If it is positioned vertically, then of course it is likely to cause more errors because the focusing and tracking servos depend on the position of the objective lens. That's why it's better when the objective lens is positioned so that gravity is the only force acting on it downwards. Okay, I think that will be explained a bit later. So aside from the voice coil assembly that I've given you an example of, where you have a coil in between magnets, so that when current passes through the coil, there is a force generated that moves the coil either outwards or inwards, and that coil is now where the objective lens is attached. There are other configurations, like you can see there in figure 46. There are several other configurations of the voice coil assembly, and all of them work on the same principle, that the error that was generated will send in current, the current will create a force, that force will push the objective lens either towards the optical disc or away from the optical disc, and in that process the error is getting corrected. Practical actuators are not rigid, so the actual structural rigidity is a key parameter in any actuator design. But it is as important to the actuator design that resonances, including unwanted rigid body modes, do not get driven. I think we all understand resonance. Resonance is not an effect that is desired in some cases. Like in this case, we do not want to have the frequency of the two frequencies being equal that will produce resonance, and resonance will now make the disc to rotate with a greater amplitude. The vibrations will be more. So if vibrations of the disc are to be avoided, then at all costs, resonance must be avoided. So this requires careful attention to the effect of all forces actuator motor, suspension, inertial and external forces on a structure and to the effect of a resonance of the sensor. So a good design rule is that forces should act through the center of gravity of a structure. Although this is often compromised in practical designs. Yeah, I think this one is already explained that it should be positioned in such a way that gravity acts on it symmetrically. We don't want to have it vertical so that the gravity will add weight on one side and leave the other. So then there we also have controllers. This is what now sends the feedback system. If there's an error, that error is compared with the input and then an action is taken. So the controller complements the above servo elements in such a way that the loop is stable and that the loop reduces given distance. Yeah, sorry about that. I think there's an issue with the internet. So in summary, this is just a repetition of what I've said, that we have two servo systems, one for the tracking, the other for the focus. The focus monitors the movement of the disk in and outwards. Tracking focus the movement of the disk along the radius. And we have photodiodes that detect the two errors. If it's moving away, the photodiodes will be able to record that and so on. So yeah, this, like I've said, is just a summary where we are saying that we have two servo systems. We have focusing servo, tracking servos. Then we have photodiodes that will use the intensity on the four photodiodes to generate an error signal, and the error signal initiates a corrective action. So then we have now the focus servo system where we have the depth of focus of the beam, which is obtained using the formula that you have here. We have the wavelength of the wavelength of the laser. Then we have the numerical aperture of the objective lens. So those two parameters are used to obtain the depth of focus. So depth of focus of a lens is the distance away from the focal plane. Okay, just look at, if you look at the diagram, you should be able to see the distance away from the focal plane over which tight focus can be maintained. So if you look at this diagram, you have a focal plane along this line. Then we have a depth of focus, which is actually on both sides. That's why we have these two here. We have these two here because we have depth of focus, which is shown here, like the two sides. So various servo systems use the optical disc system, including the focus servo and tracking servo. So it's important, this depth of focus is important so that, as we shall discuss later, the disk has several layers and there is a specific layer that contains the information. So the depth of focus determines whether the spot is actually on the correct layer or not on the correct layer. So by knowing this value, which is estimated to be about plus or minus 1.9 micrometers per CD, if the value becomes greater than this, then it simply means that there is no process of reading and writing that can take place, because the error is beyond the error that is allowed. Okay. So this one I've explained. The disk can move outwards, can be in correct position, can be towards. So those are classified as over focus, in focus, under focus, and in those scenarios, you see the shape of in the photodiode down there. You can see an oval beam. We have a circular beam at the center. That means it is focused properly. Then we have an oval, which is, elliptical. That also shows an error and so on. So the procedure of conveying the movement of the disk and the photodiode is referred to as a stigmatic aberration method. So basically what we have explained in terms of the tracking method, I mean the focusing servo, is known as a stigmatic aberration method. All right. So we have explained the different intensities, only that here this part explains using A, B, C, and D, but we have also explained it in terms of A1, A2, and so on. But the point is the same, that the quadrant photodiodes will be grouped into two, and the difference in intensities in those two pairs gives out a signal. So when you are reading and you come across this part with A, B, C, D, don't get confused, because it simply means the four quadrants. There could be some books will use Q1, Q2, Q3, Q4. Others will use ABCD. Others will use A1, A2, and so forth. But the idea is that there are four photodiodes, and intensity falls into diagonal diodes, and the difference in intensity generates an error. So tracking servo system, I've explained again, like it's a radial movement. The objective lens is forced to move outwards or inwards depending on the error that is generated. So all that you can read that, yeah, including the requirements of the pitch, the accuracy of the focusing, I mean the focus spot within the track, and so on. Yeah, so I'm trying to move a little bit fast because this is just a summary. This I've explained the diffraction part, and the tracking error signal, how it is generated, and so on. Oh, so that marks the end of it. But I think I've moved a little bit fast. So I think you'll excuse me for some slides. But what we need to do, I will send, okay, of course you're having this recording. I will send you the PDF. You go through it. I don't think it's difficult to read. I was trying to make it easier by using language that you can all understand. But I think when we meet next for a physical lecture, I will go over this handout very fast so that you can point out areas that you are not understanding. And then we explain, we discuss, and then we move to the next thing. So I encourage you, the moment you get this recording, please try to listen to it. If you need help, just note it down. We are meeting on Tuesday. I'll explain all the parts that you need you need help. So thank you very much. You can also comment on whether the audio was good, whether it was too fast, too slow, or maybe whatever I need to do to make this recording better, so that in future, if we have to make another lecture that is recorded, I will take those comments into account. So thank you very much, and have a nice day or a nice evening. Bye-bye.